So the calculations that we'll do for lenses and mirrors are going to use the same equations overall. The only real difference between doing these with lenses and mirrors is that the concave and convex, remember, are different for which one is diverging and which one's converging. But if you're referring to a diverging lens or mirror or converging lens or mirror, then all of your calculations are exactly the same, and your image characteristics then will be parallel between the two. If you're thinking in terms of concave and convex, then you'll have to be flipping them back and forth each time. So I would recommend thinking of your mirrors and lenses in terms of diverging and converging. Make sure you keep those straight for the convex and concave cases in each case. And if you do that, then all of your calculations are going to be the same, regardless of whether it's a lens or a mirror. So just a reminder then. And so make sure that you have the converging and diverging kept separate in terms of the concave and convex. And for everything else, then we'll deal with just converging and diverging when we're doing our calculations. Now there are four kind of main calculations that we're dealing with. Now your formula sheet is going to group these three together all in one, and that can be a little bit awkward overall. So we'd recommend just really thinking of them in terms of these four iterations there. So first of all, we have magnification. So magnification is going to be the image height over the object height, or the image distance from the lens or mirror over the object distance from the lens or mirror. And both of those ratios will give you then the same magnification. Now we have absolute value signs here because magnification is always going to be a positive value. If it's making it larger than the object, then you're going to have an m greater than 1. If it's smaller, it's going to be less than 1, but still greater than 0. And then if it's m equals 1, then it's going to be the same size. And that's that converging case where you're right on that center of curvature or 2f away. And so for the magnifications, then you should have those absolute value signs for each of those. So if you're just comparing the heights to the distances, we do actually get a negative sign showing up in here. And this is just going back to this bottom note here. A real image is always inverted and a virtual image is always upright. And so the HI and the DI are always going to end up having opposite signs. So we'll go into more detail on the signs in just a moment, but that's where this negative one is coming from. And so if I take the ratio of the image height to the object height and I compare that to the image distance to the object distance, now we'll know that those are going to be the same because the magnifications to those have to be the same. So if your magnification is the same, those two ratios should be the same as well. But my HI and DI are going to end up having opposite signs. So when I'm using this formula here, I do have to insert a negative sign then overall. And then the last one, we have the 1 over f equals 1 over dO and 1 over di. Now looking on our formula sheet, we see that last one, the 1 over f equals 1 over dO plus 1 over di. That one's exactly the same on this formula sheet, so that's not a big deal. This one here, though, they've grouped all these ones together. Now if I just look at this one here, the HI over HO equals negative di over dO, that one works out fine as well. My magnification equaling HI over HO, that one works out all right as well. But if I do the magnification equals di and dO, my formula sheet has this negative sign here. But just remember, this magnification is always a positive value. So if you are using this di and dO for the magnification, you do need to drop this negative sign. So the negative sign applies when you're dealing with this HI over HO equals di over dO, then you need to include the negative sign. If you're solving for magnifications though, make sure that you drop that negative sign if you're using it for the di and the dO. So just carrying on through with how these equations are used. Now again, for the most part, it's just subbing numbers into these equations. The biggest thing that you're going to have trouble with then typically is just the signs of all of those. So we have sign conventions for positive and negatives for the HIs, the DIs, and the focal points. And it's going to change for different types of lenses and mirrors. And so as long as you can keep track of the signs, then the equation should work out fine. But sign errors are the most common errors for this section. So first of all, we have our magnification. Now remember, this is always a positive value. And again, just with that di over dO case, that can be a bit confusing just because of how your formula sheet's set up. But just remember, magnification should always be positive. If your magnification is greater than 1, it's larger. If it's less than 1, it's smaller. And if your magnification is equal to 1, then it's the same size. And it's just a factor that you're multiplying the original size by to get the new size. Now f is my focal point, and that's just the distance away, and can be for a lens or for a mirror. But your focal point then is going to be a positive value if you have a real focal point. So if you have something that's converging, that's your concave mirror and your convex lens, then we have a positive focal point, and so we'll put a positive value in for that f value. Now the signs won't be given in the question, you have to put those ones in, but if you have the converging case, then your f is always going to be positive. Now that's even if you're coming up with a virtual image. If you have the converging lens or mirror, f is always a positive value. F is always going to be a negative value for those virtual focal points. And these are always going to be virtual images. But if you have that convex mirror, the concave lens, and remember that's that diverging case. If you have the diverging case, then you'll always put in a negative sign along with your focal point. Now your object distance and your object height, those ones are always going to be positive. So the object distance, the distance away from the lens or mirror, always a positive value. And your height of the object, again, always a positive value. The image distances and heights, so those can be positive or negative. So if it's a real image, remember those are the inverted ones, the image distance is going to be listed as a positive value. If it's a virtual image, those are the upright ones, the di then will be listed as a negative value. So depending on whether it's real or virtual, we'll have to put in then that negative sign or the positive sign for the di. Now for your image height, if it's an upright image, and remember the upright image is always the virtual image, we'll put in an hi value. If it's inverted, which is then always the real image, the hi is going to be negative. And so we had that kind of note here where the hi and the di are always opposite, and we see that showing up in this equation here as well. And that's because for a real image, we have a positive di, but because it's inverted, we're going to have a negative hi. If I have a virtual image, I'll have a negative di. That one's always going to be upright, and so I have a positive hi then for that. So watch your signs really carefully. Magnification, do and ho, those are always positive. But for the focal points, the image distance away from the lens or mirror, and the image height, those ones have positive and negative signs, and you have to be putting those signs in. And you'll notice this one especially has an addition in it. And so if you get the signs wrong for this one here, you won't just have the same number with the wrong sign, you'll actually have a different number. For this one here, if you're using this one, then just the sign will be wrong, but this one here, you can definitely get a completely different number just because of those sign errors. So watch those ones really, really carefully. And I definitely have this kind of sheet out always when you're working through these problems. Now, one thing I would recommend doing for any of your problems involving the curved lenses or mirrors is always be looking at what should the image actually be. And from our ray diagrams and kind of position away relative to, say, the focal point and that center of curvature or the 2f for the lenses, we should be able to come up with what the image characteristics are. No, not exact values, but at least whether it's larger, smaller, same size, upright, inverted, those sorts of things. So the first thing you want to look at is, are you dealing with something that's converging or diverging? So here we're dealing with the converging mirror. So it's going to be your concave mirror. We have a focal length of 10 centimeters. And the object is located 15 centimeters away. So what we have then is we have the converging case where we're between then that center of curvature and the focal point for the converging mirror. And those ones, if you remember, the image always forms. It's going to be real, it's going to be inverted, and it's going to be larger. Okay, so then just moving on to actually calculating then where the different values would be. We can just start with a bit of a variable list. And I'll do a variable list on these ones here because we just really want to emphasize those positive and negatives. So first of all, it's a converging mirror. So whether it's a converging lens or mirror, the focal point then, if it's converging, is always going to be positive. So this will be positive 10 centimeters then. And just make sure all your distances are in the same units. So we're 15 centimeters away. Now it's the object distance. So DO is going to be 15, and object distances are always positive. And the height of the object, again, that's also always going to be positive, then it's just going to be 5. Now what we're looking for then is both the DI and the HI, so the distance away from the mirror, and then also the height then of that image. So we can start with that focal length equation because we have the focal length and the image or the object distance, and so we can use that focal length equation then to find the image distance. So I get 1 over f equals 1 over DI plus 1 over DO. If I put my values in, I get 1 over 10 equals 1 over DI, which is what I'm looking for, and then plus 1 over 15. Move this to the other side. I get 1 over 10 minus 1 over 15 equals 1 over DI. And so for that one, then my DI will be 30 centimeters. And that's my distance then away. Then knowing my DI, I can go to that HI over HO equation. Now that equals negative di over do. Now you will notice that my di worked out to be a positive sign here. So again, watch your signs as you're going through. And so this negative then will ensure that I end up within that negative image height. And so then I have the hi over 5 can be equal to negative 30 centimeters over top of my original or object distance, which is 15. And so if I multiply those ones out, I end up then with negative 10 centimeters then for my height. And so negative 10 means then that it's going to be inverted. And so remember that for the heights. And so then we see that we have then an image that's 30 centimeters away from the mirror. And then we have then this inverted 10 centimeter height then for our image. Now for this next one as well, I'd recommend that you first start by coming up with what are the image characteristics, and then from there calculating what they actually are. So this one here, we're dealing with a convex lens. Now the convex lens, remember, it is the converging case. And you always want to make sure you're dealing, or you make sure that you know, are you dealing with the converging or diverging case. Now this one here, my focal point is going to be 6 centimeters away, and my object then is going to be 4 centimeters away. And so this one overall, once I'm looking at my lens over here, then I have my focal point over at 6 centimeters, my object is at 4, so I must be inside then that focal point. And remember, for all of those ones there, it's going to give me that virtual image. It's going to be larger, and of course then upright because it's that virtual image. And so we do have then that kind of one case then for the converging lenses and mirrors. If you're inside that focal point, you'll get that virtual upright image. In that case, then you'll always get the larger image. And so you should know that basically the characteristics of the image formed right away. And the second point, what kind of image being formed? It's a virtual image. We can answer that actually before we do any of our calculations. Everything else, so if we now want to find out the exact position of the image, then what we can do is we can take, first of all, our focal point. Now, because it's a converging lens, we are going to have a positive 6 centimeter focal point. Now, it doesn't really matter that this is going to form the virtual image. Whether the focal point is positive or negative depends on whether it's converging and diverging. The object distance then is going to be that 4 centimeters away from the lens. And so I just need to find my di value. And so I can use that 1 over focal point equals 1 over di plus 1 over do. So my focal point is 1 over 6. When I take this 1 over do and I move it to the other side, I have to subtract it to move it over. And so I get 1 over 6 minus 1 over 4. And one thing to really watch here is that we do have then the inverse, or the reciprocal for our di there. So you'll take 1 over 6 minus 1 over 4, but don't forget to take the reciprocal of that value once you have that one done. If you do that for this case here, you're going to get negative 12 centimeters, and that'll be equal to your di. Now, when you're dealing with significant digits for these ones here, we're going to be using decimal places if we're using this equation. For this one here, we're dealing with multiplication and division, the hi over ho. But for this one here, we really are adding and subtracting, and so number of decimal places is what's going to matter. These are both to 1 decimal place, and so we'll record this then to 1 decimal place then as well. And what we see then is our di is larger than our do, so we have a magnified image, so that's going to be that larger. It is negative though, so that's indicating that we have that virtual image. So for this next one, we're dealing with the mirror, and now we have a virtual image being formed. Now, if you have a virtual image being formed, remember we could have either type of mirror. So we could have either a converging or a diverging, and the difference is going to be with how large the object is. If it's getting smaller, then it's going to be a diverging. If it's getting larger, it's converging. So the original object then is 3 centimeters tall, and my image is 1 centimeter tall. So I see that I'm going to something that's smaller, and so for this one then I must have the diverging case. And for the mirror, the diverging mirror, of course, is the convex. Okay, so we have the diverging mirror is a convex mirror, so we know what type of mirror we're going to be getting, and we should then end up seeing a negative focal point. Now, our calculations should give us that, so don't put in that negative with the variable you're solving for, but we should know basically what we're looking for even before we get started on our calculation here. So then we can put in our values for these. So we have then the 6 centimeters, that's the distance away from the mirror, so that'll be my do, will be 6. My height, my HO, is going to be that 3 centimeters, and then my HI is going to be that 1 centimeter. And because it's a virtual image, it's upright, and that one then will be a positive 1 then for that value here. And so what we're going to be looking for then is our focal point. So we'll first have to come up with the DI value, and once we know the DI value, then we can use the DI plus DO to get our focal length. And again, remember, we're looking for a negative focal point, so we will be able to check our answers if we're careful with our signs. So we have HI over HO equals negative DI over DO. And we're looking then for our DI value, so we can move everything else over. And so then I'll have that 1 over 3 equals, I'm going to move the negative sign over right away. And then I have DI, and then my DO value then is going to be 6. So if I take 6 multiplied by then that negative 1/3, that will give me a DI value then of negative 2. Now I do get that negative value showing in for this one here, again still be in centimeters. I get that negative value, again, because it's that virtual image. And virtual images always have that negative DI value. So then I can go to my focal length, which is ultimately what I'm looking for here. So I get 1 over F equals 1 over DI, which is going to be 1 over negative 2. Okay, watch out, putting that negative sign in. And then plus the 1 over DO, which is then going to be my 6. So here I'm going to have actually subtraction. And again, this is where we see if we make a sign error wrong, 1/2 plus 1/6 or negative 1/2 plus 1/6 will give us different values. And so you really have to watch for the negative in this case. So when I add these two together, I will get a focal point then of negative 3 centimeters. Now watch carefully when you're solving for this one. If I take negative 1/2 plus 1 over 6, that's going to give me the reciprocal of the answer. And so don't forget to take the reciprocal when you're finding your focal length for this one here. But our focal length then here is going to be negative 3. And because it's negative, we know that it's the diverging case, which is the convex mirror. And it'll be a 3 centimeter then focal point. For this next one, we see that we have then the concave lens. Now your concave lens, remember, is going to be a diverging lens. And since it's a diverging lens, then our image characteristics are easy to come up with. It'll always be virtual, always smaller, and always upright. Now for the converging case, remember we have a number of different possible image characteristics. However, for the diverging lenses and mirrors, there's only one possible way to have that image forming. Now, how much smaller, that one can change, but they're always going to be virtual, smaller, and upright. So again, I would always go through those image characteristics before you do your calculations. One is really good just to kind of help think those ones through, and that's a good exercise to do. But also then it gives you a good way of checking if your answer makes sense then at the end as well. So because that's a diverging lens, we do have a negative focal point. So my focal length then is going to be negative 10 centimeters there. Again, make sure you're putting the negatives in with those. 3 centimeters high, that's going to be that HO value. Those are always positive. And then 15 centimeters from the lens, that's that DO value, and those ones also are always going to be positive, regardless of the type of lens. So we want the distance away, and then the size or the height of the object. So we can start with that DI value using the 1 over F equation. So 1 over F equals 1 over DI plus 1 over DO. I get 1 over negative 10, and again, negative is going to be very important to put in there. 1 over DI, which is what I'm looking for. And then I get 1 over 15. So when I move this 1 over 15 over, I get 1 over negative 10 minus 1 over 15. And that'll then equal then my 1 over DI value. So I can subtract those two. And then don't forget to take the reciprocal when you're doing that. And what you'll end up then is negative 6.0 for your DI value. And that'll be in centimeters, of course. Now don't forget that that is a negative, and we're expecting a negative because we have that virtual image. So then when I go to that HI equation, I need to carry that negative sign in. So I am looking for my HI over HO, and I have negative DI over negative DO. So my HI then over my HO of 3. Now I have two negative signs here, so watch carefully. So I have the negative just from the equation, but I also have a negative for my DI value. So I have then that negative 6. So make sure you're putting both of those negatives in because I want those to work out to be a positive because I'm expecting a positive HI for my virtual image. So this then will go over the top of that DO of 15, multiply the 3 over to the other side, and now I get my positive HI value. It'll be positive then 1.2 centimeters. So I have a distance away of 6 and a height then of 1.2. Now the other thing to remember, it must be smaller. So I have 1.2, whereas my original object was 3, so it is smaller. It's positive, which I'd expect for my virtual image then as well. And so it does check out to the characteristics I'm expecting from that diverging lens. So for this one here, we're told that we have a focal length of 3 centimeters, and we're specifically saying positive 3. So we are looking at then the converging case for this. And so for the mirror then, that's going to be that concave mirror. And we're looking for to produce an image that's going to be 1/8 of the object size. So we want something that's going to be smaller. And so we're dealing then with that concave mirror. We have our focal point, and we have then our center of curvature. And if we're looking for something that's 1/8 the size, then our object has to be outside then of that center of curvature. So we are going to be looking for something then that's going to be beyond the 6 centimeters. So your focal length is going to be 3, your center of curvature then must be 6. And if we want to produce then that smaller image using then a converging mirror, we must be beyond then that center of curvature. So we'll start with our variable listing here. Now we don't know actually a lot about the variables. So our focal length here is going to be positive 3. I really don't know very much about the other characteristics. Magnification of 1/8, but my DI and my DO are both unknown. However, I have that relationship between them. So I have the magnification is going to be equal then to DI over DO. Now remember, for this one I do drop that negative sign because my magnification should always be a positive. And so then I have 1/8 equals DI over DO. And I can isolate either one, but I'll just have DO over 8 is equal then to my DI value. So I have that relationship then between those. Then I can go to my focal length equation. So I have 1 over my focal length equals 1 over my DI plus 1 over my DO. Now this one here is currently within 3 variables. I know what my focal length is though, and I know the relationship between those. So I'm going to solve this one as a system of equations. I'll put in the 3 for my focal length, and then I'll just write these ones in terms of a single variable. Now you can solve for your DI or your DO. Since we're looking for where we're going to place the object, I'm going to sub in for my DI, for my DO, and that way then I have my DO that I'm already solving for. But you could also sub in for DO, solve for DI, and then work backwards to the answer, and that would be fine as well. So I have 1 over 3. Now my DI is DO over 8, so I get 1 over DO over 8. And then 1 over DO, which is again the unknown. Now this one here, I get 1 over 3. Now this here just is going to go to 8 over DO. So remember, you just multiply by the reciprocal to get then those complex fractions worked out. And so then I get 1 over DO. Now I do have a common denominator here, and so I can just add these. So I get 8 plus 1. So I'm going to get 1 over 3 equals 9 over my DO value. And I just need to multiply my DO to this side and my 3 to the other side, and my object distance, then we'll see, is going to be 27 centimeters away. Now again, that's going to be well outside of the center of curvature, and my focal length is 3 centimeters. To be outside of that center of curvature, I just need to be more than 6 centimeters away, and so that is a value that we're expecting. If you put 27 centimeters away, then you'll get that 1/8 then magnification.